Hi, welcome back. This is the second session on transfer of mathematical structures using bijections. Hopefully, this will be a shorter video. Okay, so let us get to the job. So, as I said, there is an article with the same title which was written about 2 years ago. You can get it by email request. You mention your names, course of study, and the name of the institution where Tuition tuition where you study. Okay, right, let's get started. And I'm recording. Yes, okay. So now let's again start work with the same thing. Yeah, so the map was here from R to R given by f of is equal to x plus 1, right? Okay, so we had already transferred, okay, the structure of this is the scalar multiplication, okay, to R on the domain, on the codomain, right? Okay, now what we want to do is we want to transfer the multiplication operation on the domain to the codomain and check whether the codomain becomes a field. Okay, let us do that. So let me start with the codomain. This is domain, this is codomain, this is domain. Start with me y1 and y2. I want to define multiplication y1 star y2. How do I do that? Notice that this is not scalar multiplication, this is a different notation. Okay, this y1 correspond to y1 minus 1 and y2 correspond to y2 minus 1. Therefore, what is the recipe? Recipe is do the multiplication here, that is y1 minus y1 into y2 minus y1, sorry, y2 minus 1, which is y1 y2 minus y1 minus y2 plus 1. And where does that goes to? On the codomain it goes to y1 y2 minus 1 minus y2 plus 2. You will remember the picture, whatever I want. Okay, do look at their thing, and this is their multiplication. Okay, let me use a different notation. This is your multiplication, this is y1 y2, this is x1 x2, this is my x1 x2, and so I have this one x1 x2 goes to this, which is f of x1 x2, which is what I denote by y1 star y2. You understand this? So let me write, therefore on the codomain, okay, what is the multiplication? y1 star y2 is y1 y2 minus y1 minus y2 plus 2. Okay, notice that in the earlier thing I defined lambda y, okay, which in the codomain lambda star of y. Okay, that and this will be different. Okay, you should notice that they are not the same. Okay, so that is why I am using the same thing which we did. Usually I do use a different notebook. I try to use the same notebook. Let us see that. See, you see that lambda star of y, that is, think of this as y1 y2, then y1 y2 minus y1 and plus 1. Okay, and here it is different. So even though I used the same star notation, this is for a scalar multiplication, whereas this is multiplication of two elements. Multiplication on the codomain, not scalar multiplication, right? Okay, so you can check y2 star y1 is same as y1 star y2, obvious, and y1 star y2 star y1, again you can do that. Okay, I am not going to that, just check associativity. What is the multiplicative identity on the codomain? Okay, Gus is f of 1, but what is f of 1? That is 1 plus 1, which is 2. How do I check it? Let us look at. So start with any y in codomain, y star 2, let me do, that is going to be y1 y2, that is 2y, minus y minus 2 plus 2, which is y. Just go back, y1 y2, that is here it is y and 2, if you want to make it 2 and y, so 2y minus 2 plus 2, so that gives me y, you understand? And similarly 2 star y. So 2 is the multiplicative identity on the codomain. Okay, what is the inverse? Give me a y and y. What is the multiplicative inverse? Right? So start with a y. Where does it go to? It goes to y minus 1. And y minus 1, what is the multiplicative inverse? 1 by y minus 1. Where does it correspond to? 1 by y minus 1 plus 1. This is y by y minus 1. Notice that this y cannot be equal to 1. Why? Because 1 is the additive identity. Identity on the codomain. Okay, so only non-zero elements, the non-zero elements simply means my real number y on the codomain should not be equal to 1. Therefore this makes sense. This makes sense because y is not equal to 1. Are you following? Now let us check, okay, whether y star y by y minus 1, whether it is equal to 2. This is the multiplicative identity, right? But what is this? This by definition is ordinary multiplication, y into y minus 1, that is by 1, minus y by y minus 1 plus 2. So you see that, go back, y1 y2 minus y1 minus y2 plus 2, that's what I am writing. Okay, so start with y minus 1 as a common denominator, therefore it's y squared minus y into y minus 1 minus, it is y minus 1, minus y plus 2 into y minus 1. Okay, you can see this is y squared cancel, this is plus y, that cancel, therefore I am left with 2 into y minus 1 by y minus 1, which is equal to 2. So now you can see something very interesting. What is that? On the codomain, okay, I have R, I have a dagger, I have a star, and it becomes a field. And what is y1 dagger y2? I don't remember, but let me see. y1 correspond to x1 minus 1, and y2 correspond to this one, x1 plus x2 minus 2, and that goes to x1 plus, okay. This is by definition y1 plus y2 minus 1. You see that? You should become confident about such things. Let us go back and check whether that's what we had. See, y1 plus y2 minus 1. Is that correct? Okay. Right. And y1 star y2 equal to y1 y2 minus y1 minus y2 plus y2. So just imagine yourself, I take the real number system R and define this new addition dagger and the new multiplication star, okay, which uses of course the standard multiplication on R and standard addition on R and the standard additive inverse, etc. Okay, if I use this and ask you to check it's a failed with respect to these operations, you can check, but you will be bewildered. How did anybody think of these operations? You see that power? Yeah, this is some kind of, okay. Now we also do that in a reverse engineering. Okay, I will explain that in a minute. What is meant by reverse engineering? You might have heard in software industry what is reverse engineering. Okay, some software is given and you just try to find out how what the script or program, okay, which makes it work. So you reverse engineer, right? So similarly we are going to do a reverse engineering. Let us do that. Suppose let us look at complex numbers. So from high school I know complex numbers are written as x plus iy, where x and y are real and z is uniquely determined by the real part x, which is real part of this, and y, which is the imaginary part of z. Okay, that what does it mean? If you write x plus iy equal to something like a plus ib, these are equal if and only if x equal to a and y equal to b. This is the notation, right? Now what I want to do is I have a bijection of C with R2. Okay, what is a bijection? You start with a complex number and send it to real part of z and imaginary part of z. Okay, let me write z equal to x plus iy. Okay, right, this is a bijection. Yeah. Now using the bijections, call this a bijection f. Using f, we transfer the field structure on C onto R2. You know, if you go to master's degree, you will see the first lecture on complex analysis will be, okay, complex numbers is R2, ordered pair of real numbers x and y with addition and multiplication defined the following way, and check it's a field. Okay, how did they get it? By this reverse engineering. We are going to see that what it means. Okay, so how do I do that? Suppose z is x plus iy and w is u plus iv. Then what is z plus w? In high school we define it as x plus u plus I times y plus v. Therefore under bijection what does it mean? F of z plus w, where does it go to? It goes to x plus u and y plus v. Therefore we define, okay, xy as uv as x plus u plus y plus v. Just don't get confused. That's the way we always did in R2. That don't remember. Okay, I am defining an R2, okay, which is ordered pair of real numbers x, y and addition. What is addition? This is the definition of addition. This you already know because you already learned vector spaces, linear algebra, etc. But just pretend this is the way we are defining. The next thing, how will I define multiplication? Z times w, that will be x plus iy. I do the usual high school way. This is xu plus x times I, therefore I times xv plus I times yu minus yu. I into I, therefore minus y. Therefore this is xu minus yv, yv, okay, plus I times xv plus yu. Therefore if you give me two elements xy and uv in R2, okay, I want to define the multiplication on R2. This by definition I am going to say this is nothing other than xu minus yv and xv plus yu. Okay. Now you want to check R2 with respect to this addition and with respect to this multiplication is a field. And this field is known as complex field, complex number field. This is how you will do in MSc. Okay, it looks as though very strange, but this is what we do. Just for fun, let us see what will be I. Okay, the I will correspond to, remember, it is 0 plus 1I, therefore it will correspond to 0 1 in R2. Right? Therefore, let us see 0 1 cross 0 1. What will it be? Go through the definition. This is your x, y, u, v. That is xu is 0 and yv is also 0 and then x, yeah, I hope, no, sorry, xu minus yv. Y is this, v is this, therefore it is minus 1. Minus 1, right? This into this is minus, which is 1. Next is xv. Xv is 0, yu is also 0, therefore 0. Okay, you see that? That means if I think of this I times I is minus 1 because I am going to identify R as in R2 by any real number x goes to x comma 0. That's very correct because if I have a real number x in R which is subset of C, how will I write x? X I will write as x plus 0 times I, right? I times 0. Therefore, where will it correspond to? X comma 0. Do you understand this? Please spend some time and okay, when you come to MSc you will learn all these things. So let me just pause, review, proceed. Please go through the construction of complex numbers. Again you can ask the same questions. What is the multiplicative identity? And if I take a non-zero element xy, when is a non-zero element? The corresponding complex numbers x plus iy must be non-zero. That means x is non-zero, y is non-zero. Then what is the multiplicative inverse of xy in R2? Right? You will find the usual formula. It will be fun. I hope you take it as an exercise. If you do that on your own, you would have mastered this. Okay? Okay. Now I come to the last bit, how to transfer some mathematical structures other than algebra. So far whatever I did, you see that I define 5 binary operation how to transfer, and if it's a group, how the group structure gets transferred, if it's a vector space, how the vector space gets transferred, and if it's a field, how the field is get transferred. You understand? So this is what we did. Just to impress upon you, let me ask you to think about this. You may know the set of real numbers are the set R2, that is set of ordered pairs of real numbers. They have the same cardinality. What does that mean? That there is a bijection F from R on to R2. Yeah? Right. Now do you see the fun? This bijection is, okay, we know it exists, but we don't have a concrete description of this bijection. Suppose it is there, okay, I can transfer the one-dimensional vector space structure on R onto R2. Therefore, R2 becomes a real vector space of dimension 1. Or other way around, transfer the vector space structure on R2, which is two-dimensional real vector space, onto R. Therefore, R, okay, with a new addition, new scalar multiplication, will become vector space of dimension 2 over R. Isn't it very surprising? So this is what actually the isomorphism does. So as I said in the first session, okay, isomorphism says you can remove the disguise, camouflage. Okay, you understand that? You remove that, it is trying to wear a mask, remove that, then you see it is nothing other than something which you already know. Okay, look at these examples, go through once or twice, discuss with your friends, you will become a master. Okay, let's go back. Now let's transfer the structure. Okay, now suppose let us look at my x is minus 1 to plus 1. Right? Now I want to define a thing. Notice that I have a bijection of this into R. What is the bijection? The standard trick is I would like 0 to go to 0, and see, it's not minus 1 is not there, but intuitively minus 1 should go to minus infinity and 1 should go to plus infinity. That is, as I go, x goes to minus 1, the image f of x should go to minus infinity. That's a very precise way of writing. When x goes to 1, f of x goes to plus infinity. Okay, this is the precise meaning. Okay, how do I construct such a map? So I want 0 to go to 0, therefore t going to t, right? But what do I want? I want as t goes to 1, I want to say, okay, suppose I define f of t, then f of 0 will be 0. But what do I want? As t goes to 1, I want f of t goes to infinity. Okay, but t will go to 1, therefore what do I do? T by 1 minus t. But then as t goes to minus 1, I want f of t should go to minus infinity. Therefore what do I do? I will make sure 1 by 1 mod t, as t goes to minus 1, mod t goes to 1, therefore this will go to 0. But then numerator t will be negative, therefore I give this. You understand? Please go through this. So we define f of t equal to t by 1 minus mod t. Then f from minus 1 to plus 1 to r is a bijection. Pause, review, proceed. Right? Now I define a metric d on, see, remember minus 1 1 is already a subset of r, therefore given any r and s here, r s in the interval minus 1 to plus 1, I can define the distance to be a r minus s. This is a standard induced definition, right? I want to induce a new definition. See, r already have a metric, therefore what I do is distance between, okay, s and t is distance between fs and ft. What does that mean? This is modulus s by 1 minus mod s by t by 1 by mod t. Okay, this is my definition. So this d, therefore this d is a metric on minus 1 to plus 1. So what did I do? I transferred the structure of, okay, we transferred the metric structure on the codomain to the domain. Okay. Okay, pause, review, proceed. We are going the other way around today. I could also do the other way, okay, by constructing the inverse of that. G is the inverse of r to minus 1 to plus 1, where G is f inverse. I can do that also. But I want you to think the other way around also. Are you following what I am saying? So far, I transferred the structure on the domain onto the codomain. Here I am trying to define the other way around. Start with the structure on the codomain and transfer it to the domain, so that you get used to this way of thinking. Okay, in my article you will also see how to do this. Okay, now let us look at R. With this distance, we know it's a complete metric space. That is, every Cauchy sequence converges. Right? Therefore, I conclude, therefore, now notice this f from minus 1 to plus 1 to r, this metric, induced metric, with this standard absolute value metric, this is an isometry. Okay, what does it mean, isometry? The distance between r and s is same as distance between f of r and f of s. But that's how we define. You understand that? This is an isometry if this happens. X to y metric spaces. F is an isometry, mean distance between x1 x2 must be equal to distance between fx1 and fx2. Right? But the way I define the metric on this is by using this. Therefore, it's by definition it's an isometry. Therefore, if you start with any Cauchy sequence xn in the domain, then f of xn is Cauchy. In x, then f of xn is Cauchy in y. This is my y, this is my x. Right? And this is complete, therefore f of xn converges to some y, and if x is such that f of x equal to y, then my xn will converge to x. Why? Because distance between x and x is same as distance between fxn and fx, but that goes to 0, therefore this goes to 0. You understand that? Pause, review, proceed. Okay, therefore minus 1 1 with this new metric, okay, is complete metric space. Let us look at, you may wonder, let us look at a sequence xn which converges to 1. For example, 1 minus 1 by n, which is n minus 1 by n. Right? So this converges to 1 in the usual metric. But we say this object, this xn equal to n minus 1 by n, this sequence is not Cauchy in this metric, in this new metric. Why? Let us look at distance between n minus 1 by n and m minus 1 by m. Let us assume n is greater than m if you want. Okay, what is this? This distance is by definition. What is the distance? You just see that. What do I do? N minus n by 1 minus, this is a positive, therefore I can write 1 minus n by n minus m minus 1 by m by 1 minus m minus 1 by m. Go to the definition, t by 1 minus mod s, right? S by 1 minus mod s, t by 1 minus mod t, right? So let us simplify. Therefore this is n minus 1 by n into, this is going to be n minus 1 by n, therefore it is going to be n by 1, right? Minus similarly m minus 1 by m into m by 1, but that's going to be distance between n and m. Okay, this is not Cauchy. Yeah. So what, this is just to make sure we know this one is complete. Okay, but what I want to show is there is an obvious sequence which converges to 1, therefore it will be Cauchy in the standard metric. That is, okay, if you want, think of this, xn is Cauchy in the standard metric, the usual metric, right? But you want to say it is not Cauchy in this metric, therefore, okay, absence of 1 and minus 1 do not matter. Okay, don't get confused, think about this carefully, right? The same thing, if you know something about topology also I can define. I will say it and stop. I can do a lot more. Suppose x tau is a topological space, or simply x is a set. Okay, x is a set, y is a topological space. Okay, there is a bijection of the set x to y. Right? Now I want to define a topology tau x on x, that is transfer the topology on y to a topology on x using the bijection f. How do I do that? Start with a u. I declare this is open if and only if f of u is open in y. Okay, then this collection tau of x, which is u subset of x, okay, f of u is open. This is a topology on x, and f from x tau x to y tau y is a homeomorphism. Okay, I leave the details to you. This is very easy. Okay, because it's already a bijection. It is also continuous because you start with a view open, then inverse image of that will be open, and it's also an open map by very construction. Therefore, it is a homeomorphism. Okay, these are all easy. And if you are a BSc student, you simply ignore. So, the basic idea, I wanted to illustrate two things. What is the first thing? So let me summarize. Okay, if x and y are sets, if f is a bijection from x to y, if there is a mathematical structure on any one of them, maybe on x, maybe on y, I can transfer that structure onto the other set using the bijection f. Okay, right? Okay, this is how you construct some very weird looking examples of vector spaces or groups or fields, or even identify complex numbers as pair of real numbers with a very kind of a mysterious multiplication, right? X comma y start u comma v equal to something. Okay, these are the things. This is essentially reverse engineering. Okay, I hope you enjoyed. Please go through it, and this should explain the purpose of why isomorphisms are important. Think about it. We will meet again.